Let's start with the mean value theorem. It says that if a function f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there must exist some point c in between where the instantaneous rate of change equals the average rate of change over the whole interval. In symbols, derivative of f at c equals the quantity f of b minus f of a divided by the quantity b minus a. This connects to the first derivative test for classifying critical points. If the derivative of f changes from positive to negative at a point c, that point is a local maximum. If it changes from negative to positive, that point is a local minimum. Now, the general procedure for optimization problems. First, identify the quantity you want to optimize and write it as a function of a single variable. Second, use any constraints given in the problem to eliminate extra variables. Third, differentiate that function and set the derivative equal to 0 to find critical points. Fourth, classify each critical point using a derivative test or by checking endpoints. Let's apply this to a worked example. We have an open-topped box with a square base of side length x and height h. The volume must equal 32, and we want to minimize the surface area. The constraint is that volume equals x squared times h, and this must equal 32. Solving for h, we get h equals 32 divided by x squared. The surface area, since the top is open, is the base plus the four sides. That gives S equals x squared plus 4 times x times h. Now substitute h into this formula. Since h equals 32 divided by x squared, 4 times x times h becomes 128 divided by x. So surface area as a function of x is S of x equals x squared plus 128 divided by x. Differentiate this with respect to x. Derivative of s by dx equals 2x minus 128 divided by x squared. Set this derivative equal to 0 to find the critical point. That gives 2x equals 128 divided by x squared. So 2 times x cubed equals 128. So x cubed equals 64, and therefore x equals 4. To confirm this is a minimum, check the second derivative. D squared s by dx squared equals 2 plus 256 divided by x cubed. At x equals 4, this evaluates to 2 plus 4, which is 6. Since 6 is greater than 0, this confirms a local minimum. Now go back and find the actual dimensions and minimum area. With x equals 4, h equals 32 divided by 16, which is 2, and the minimum surface area, s of 4, equals 16 plus 32, which equals 48. Here is a useful trick for related rates and optimization problems. Before touching any equation, write down, as an explicit labeled list, every quantity you are given, along with the quantity you are solving for. This takes the burden of tracking everything off your working memory and lets you focus purely on the algebra. Now, the most common trip-up in related rates problems. Students often substitute the known numerical values into the equation before differentiating instead of after. This is a serious error because plugging in a number turns a variable into a constant, and once you differentiate a constant, you get 0, silently destroying the very rate of change you were trying to find. So the teaching tip is this: enforce a strict written order every single time. Differentiate first and substitute numbers second. Keep the entire equation in symbols all the way through the differentiation step, and only plug in the specific numerical values at the very end once the derivative has already been taken.